Topic of the lecture is information and mutual information. Suppose a die has faces 1 and 4 with red color and faces 2, 3, 5 and 6 with black color. Now, suppose this kind of die was rolled and we were told that the outcome was 4. Clearly, we were given all the information concerning the outcome of the experiment. If we were told that the outcome was red, we would agree that we were given some information, but not all. The outcome is narrowed to one of two possibilities. On the other hand, if we were told that the outcome was black, we would feel that we were given some information, but even less. The outcome is narrowed to one of 4 possibilities. Another example, suppose after 6 weeks of the semester, students were told that there will be a 1-hour examination. Clearly, such an announcement contains a certain amount of information. However, if the students were told after 1 week of classes that there will be a 1-hour examination, we would say the announcement contains much more information because it is quite unexpected that an examination would be scheduled after only 1 week of classes. So, this is a surprising statement. So, that is why it will contain more information. So, from these examples, it is clear that it is very important to measure quantitatively how much information a certain piece of message carries. If a statement tells us the occurrence of a certain event that is likely to happen, we would say that the statement contains a small amount of information. On the other hand, if a statement tells us the occurrence of a certain event that is not likely to happen, we would say that the statement contains a large amount of information. So, this observation suggests that the information contained in a statement asserting the occurrence of an event depends on the probability of occurrence of the event. The information content of a statement asserting the occurrence of an event is minus log p, where p is the probability of Since p is always less than or equal to 1, minus log p is always positive. It is also clear that the smaller the value of p, the larger the quantity minus log p. This implies if the probability of occurrence of an event is less, the statement asserting the occurrence of an event will contain large amount of information. Thus, if we now consider the example by which we started, when we were told that the outcome of rolling a die was 4, the amount of information we received is equal to minus log 1 by 6, and that is log 6, which is 2.585. On the other hand, when we were told that the outcome was red, the amount of information we received equal to minus log 2 by 6. Because if red has occurred, then the probability will become 2 by 6, because there are two possibilities only, 1 and 4. So, that is why number of favorable cases will become 2, and that is why the probability will become 2 by 6, and as a result of this, amount of information will be minus log 2 by 6, and that will be log 3, which is 1.585. Another example, suppose that we receive from the computer as output a binary digit that is either 0 or 1 with equal probability of occurrence. When we are told that the output is indeed 1, the amount of information we receive is minus log half, because there are only two possibilities, 0 and 1. So, that is why probability will be 1 by 2, and the amount of information will become minus log half, that is 1. Similarly, when we are told that the output is 0, the amount of information we receive is also minus log half. So, it will be 1. Now, suppose we receive 32 binary digits from the computer as output. Assuming all 2 to the power 32 possibilities are equally likely, the information we receive is minus log 1 by 2 to the power 32. So, there are all total 2 to the power 32 possibilities. So, the probability, and they are equally likely also. So, that is why the probability will become 1 by 2 to the power 32. So, the amount of information will become minus log 1 by 2 to the power 32, and that is 32 bits. So, the amount of information we are getting 32 bits. At this stage, I would like to introduce the notion of mutual information. Suppose we were told that the outcome of rolling a die is red. How much does that help us to determine that the outcome is a 4? Suppose we were told that the professor will be out of town tomorrow. How much does that help us to determine that there will be a 1 hour examination tomorrow? So, this kind of questions can be tackled by mutual information. Thus, we want to know the amount of information concerning the occurrence of event A that is contained in the statement asserting the occurrence of event B, which we shall denote by I of A B. Since minus log probability of A is the amount of information contained in a statement asserting the occurrence of event A, and minus log probability of A given B is the amount of information contained in a statement asserting the occurrence of A given that B has occurred. The difference between these two quantities is the amount of information on the occurrence of A provided by the assertion that B has occurred. In other words, we need minus log probability of A bits of information to assert the occurrence of event A, and we still need minus log probability of A given B bits of information to assert the occurrence of event A after we were told that event B has occurred. Thus, the information provided by the occurrence of event B on the occurrence of event A is I of A B, that is I of A comma B, that is equal to minus log P of A, that is minus log probability of A, minus log probability of A given B. So, this is the conditional probability. So, this is equal to minus log probability of A plus log probability of A given B. For example, let A be the event that 4 appeared and B be the event that red appeared when a die was rolled. Then I of A comma B is equal to minus log probability of A plus log probability of A given B. So, this will be equal to minus log 1 by 6, because here the event A is that 4 has appeared. So, there are 6 possibilities 1, 2, 3, 4, 5, 6, among that 4 has occurred with probability 1 by 6. And log probability of A given B. What is this? It is given that red has appeared. So, this event is given. So, in that case we will have only 2 possibilities 1 and 4. So, that is why the probability that A given B will become half. So, this will be log half. So, we will get 2.585 minus 1, and this value will be 1.585 bits. Now, if we replace the event B by the event C, that an even number appeared, then what will happen? So, B is replaced by C. So, that is why we have to find I of A comma C, and that is equal to minus log probability of A plus log probability of A given C. So, minus log probability of A, that is same, that is minus log 1 by 6 plus, now what is probability of A given C? If it is given that even number has occurred, so that means there are only 3 possibilities, 2, 4 and 6. So, in that case 4 will occur with probability 1 by 3. So, that is why this will become log 1 by 3. So, we will get 2.585 minus 1.585, which is 1 bit. So, from this we can observe that if probability of A given B is large, it means that the occurrence of B indicates a strong possibility of the occurrence of A. Consequently, I of A comma B is large. However, if probability of A given B is small, it means that the occurrence of B does not tell us much about the occurrence of A. Consequently, I of A comma B is small. As a matter of fact, the occurrence of event B may mean that event A is less likely to occur. In that case, probability of A given B is smaller than probability of A, and I of A comma B becomes negative. Let us also examine some extreme cases. Suppose that B is a subset of A in S. In that case, intuitively the occurrence of B assures the occurrence of A. Since we have probability of A intersection B is equal to probability of B, it follows that probability of A given B is equal to 1 and minus log probability of A given B is equal to 0. That is the mutual information provided by the assertion that B has occurred on the occurrence of A is equal to the information provided by the assertion that A has occurred. However, suppose that B is the whole sample space. In that case, probability of A intersection B is equal to probability of A and minus log probability of A given B is equal to minus log probability of A. and I of A comma B is equal to 0, and this means that occurrence of B tells us nothing about the occurrence of A. So, here we take one example. Consider the problem of estimating the likelihood that there will be a 1 hour examination when the professor is scheduled to go out of town. Let S is the set containing x 1, x 2, x 3 and x 4. This is the sample space where the samples represent the 4 possible outcomes. Now, this can occur in 4 possibilities only. Professor is out of town and examination is given. So, that is considered as event x 1. Probability professor of out of town and examination not given. So, that is considered as x 2. Professor in town and examination given, that is x 3, and x 4 represents professor is in town and examination is not given. So, there are 4 cases which are possible here. Now, another thing we are considering the probabilities also, probabilities of x 1, x 2, x 3, x 4. Probability of x 1 is considered as half, probability of x 2 is 1 by 16, probability of x 3 is 3 by 16, probability of x 4 is 1 by 4. Let A denote the event that an exam is given and B the event that the professor is out of town. Note that probability of A is equal to half plus 3 by 16. So, probability of A means probability that an exam is given. Probability, what is the probability that an exam is given? So, that probability is probability of A, and we know that we have 2 cases here, x 1 and x 3. So, that is why we have to add probability of x 1 and probability of x 3. So, that is why it is half plus 3 by 16, which is 11 by 16. Now, next we are finding the conditional probability of A given B. So, that is probability of A intersection B divided by probability of B. Now, what is probability of B? B is the event that professor is out of town, and that is occurring in 2 places, x 1 and x 2. So, that is why to find the probability of B, we have to add the probability of x 1 and probability of x 2. So, that is here in the denominator, and in the numerator it is half, because it is probability of A intersection B, that is both A and B will occur. So, here A and B, that is exam is given and professor is out of town, both these events is occurring here. So, probability of x 1 we have to consider in the numerator. and if we simplify this, we will get the value 8 by 9. The information needed that an exam will be given is minus log probability of A. So, it is minus log 11 by 16 because probability of A is 11 by 16. So, this will be minus log 11 plus log 16 and that will be minus 3.46 plus 4 which is 0.54 bits. And the information that professor is out of town on the fact that an exam will be given is I of A comma B is equal to minus log 11 by 16 plus log 8 by 9. How is it coming? Here A is the event that an exam is given and B is the event that professor is out of town. So, we are trying to find the mutual information of A and B. So, that is I of A comma B which is minus log probability of A plus log probability of A given B. Now, minus log probability of A will become minus log 11 by 16. Now, what about probability of A given B? That we have already found, that is 8 by 9. So, it will be log 8 by 9 and that is why the resulting value will be 0.37 bits. Let C denotes the event that the professor is in town. Then probability of A given C will become probability of A intersection C divided by probability of C. Now, probability of C is the probability that the professor is in town, and if we see the cases, professor is in town in two cases x3 and x4. So, we have to find the probability that professor is in town, and for finding this we have to add probability of x3 and probability of x4, and that is what we are doing here. So, it will be 3 by 16 plus 1 by 4, and in the numerator both the events will occur, that probability. So, probability that A and C will occur. So, exam is given and professor is in town, that probability, if we consider the cases again. So, that is occurring here, professor is in town and examination is given. So, x3. So, that means we have to take the probability of x3, that will be 3 by 16. So, if we simplify this, we will get 3 by 7. So, we will have I of A comma C, that is the mutual information taking these two events, concerning these two events, that is minus log 11 by 16 plus log 3 by 7. and that is minus 0.69 bits. The fact that the professor is in town makes it less likely that an examination will be given. So, if we see, so probability of A given C, this is 3 by 7, but probability of A given B, it is 8 by 9. So, from this we can conclude this, that professor is in town makes it less likely that an examination will be given. Consequently, the mutual information provided by the presence of the professor on the occurrence of an examination is a negative quantity. So, that we have already observed, that is minus 0.69. So, the mutual information is very less. Now, let us consider one example here. Let us draw the figure first. So, this is the transmission end and this is the receiving end. This is a simple model of a communication channel known as the binary symmetric channel. At the transmission end, either 0 or 1 is transmitted, and at the receiving end, either 0 or 1 is received. Specifically, when 0 is transmitted, zero will be received with probability 1 minus epsilon. When 0 is transmitted, 1 will be received with probability epsilon. When 1 is transmitted, 0 will be received with probability epsilon. When 1 is transmitted, 1 will be received with probability 1 minus epsilon. So, this kind of communication channel we are considering. Suppose we have two equally likely messages M1 and M2 that will be transmitted over the channel using the representations 0 0 0 and 1 1 1 respectively. If 0 1 0 was received, we can compute the mutual information transmitted and the event that either part or the whole of the sequence 0 1 0 was received. So, if 0 1 0 was received, we are trying to find the mutual information between the event that message M1 was transmitted and event that either part or the whole of the sequence 0 1 0 was received, and that will be I of M1 comma 0. Now, what is this? This will be minus log the probability that M1 is transmitted plus log the probability that 0 was received, given that 0 was received, the probability that M1 was transmitted. So, this value we can calculate in this way. This minus log probability of M1, that will be minus log half, because M1 and M2 are equally likely. So, there are two possibilities, M1 or M2. So, that is why it will be half, probability will be half. So, that is why this value will be minus log half. Now, what about this conditional probability? This we have to find. So, probability that M1 given 0, and this we know it is probability that M1 intersection 0, both these events will occur. M1 is transmitted as well as 0 is received, this probability, and in the denominator probability that 0 is received, and this can be written as probability that M1 intersection 0 divided by probability of M1 into probability of 0 given M1 plus probability of M2 into probability of 0 given M2. Because this is probability of 0, this is nothing but the total probability. So, because there are two possibilities M1 and M2, so that is why either M1 or M2 will occur. So, probability of M1 into probability of 0 given M1. So, this is the probability that M1 is transmitted, that is given. Then what is the probability that 0 is received, and next is probability of M2 into probability of 0 given M2. Now, probability of 0 given M2 is the probability that it is given that M2 is transmitted, then what is the probability that 0 will be received. So, this numerator can be written as probability of M1 into probability of 0 given M1 divided by probability of M1 into probability of 0 given M1 plus probability of M2 into probability of 0 given M2. So, these probabilities we have to find. Now, the numerator, if you consider, it will be probability of M1 into probability of 0 given M1. Probability of M1 is half and probability of 0 given M1, that will be 1 minus epsilon. So, M1, given that M1 is transmitted, 0 will be received with probability 1 minus epsilon. Okay. So, this will be half into 1 minus epsilon. Now, in the denominator we will have probability of M1. So, same whatever we are writing in the numerator, this one is also same. Now, the other one, that will be half into epsilon. So, we will get I of M1 comma 0 is equal to minus log half plus log half 1 minus epsilon divided by half into 1 minus epsilon plus half epsilon. So, finally, we are getting the value 1 plus log 1 minus epsilon. Next, we are considering I of M1 comma 0 1, because we are trying to find the mutual information between the event that M1 is transmitted and the event that the whole sequence 0 1 0 or part of it is received. So, one part we have already considered, that is 0. Now, we are considering another part, that is 0 1. So, I of M1 comma 0 1, this will be minus log probability that M1 is transmitted plus log probability that 0 1 is received, then the probability that M1 is transmitted. So, this conditional probability, log of this conditional probability. So, let us find M1 given 0 1. This will be probability M1 intersection 0 1 divided by probability of M1 into probability of 0 given 0 1 0 given 0 1 given. So, let us write it freshly here, M1 given 0 1 that will be probability that M1 intersection 0 1 divided by probability of 0 1, which is probability of M1 into probability of 0 1 given M1 divided by probability of M1 into probability of 0 1 given M1 plus probability of M2 into probability of 0 1 given M2. Now, the numerator probability of M1 is again half, and this conditional probability will be 1 minus epsilon into epsilon. So, M1 given that M1 is transmitted, that means 0 0 0 that is transmitted. So, from 0 0 will occur with probability 1 minus epsilon, and from 0 1 will be received with probability epsilon. So, that is why this we are getting. In the denominator we will have half into 1 minus epsilon into epsilon plus this also will give the same expression, half into epsilon into 1 minus epsilon. So, this value will become half, and as a result of this, I of M1 comma 0 1 will be minus log half plus log half. So, this mutual information is equal to 0. In the same way, if we find I of M1 comma 0 1 0, that will be minus log half plus log half into 1 minus epsilon whole square into epsilon divided by half into epsilon into 1 minus epsilon whole square plus half into epsilon square into 1 minus epsilon. So, this one will give 1 plus log of 1 minus epsilon. So, knowing that either 0 or 0 1 0 was received tells us exactly the same amount of information on the transmission of message M1. However, knowing that the sequence 0 1 was received tells us nothing about the transmission of message M1, and this is why what we expect, this is actually expected, because the transmission of either M1 or M2 would yield the sequence 0 1 at the receiving end with the same probability. So, now let us discuss one result of mutual information. I of A comma B is equal to minus log probability of A plus log probability of A given B, and that is equal to minus log of probability of A minus log probability of B plus log probability of A intersection B, because probability of A given B is probability of A intersection B divided by probability of B. So, we can write this as minus log probability of B minus log probability of A plus log probability of A intersection B. So, it will be minus log probability of B plus log probability of A intersection B divided by probability of A, and that is equal to minus log probability of B plus log probability of B given A, and this is nothing but I of B comma A. So, this implies mutual information is a symmetric measure in the information concerning two events. Thus, I of A comma B is a measure of the mutual information from B to A as well as from A to B. And that is all. Thank you.